In this video I'm going to go over question 2 of the 2015 C3L6 paper. So once again I recommend that you have a go at this question before watching the video. The link is going to be in the video description. This question uses skeletal formulae throughout, and there's a very brief introduction to them in this part of the question. However, there is also a document specifically on skeletal formulae on the download section of the C3L6 where all the papers are as well, so I recommend you have a read through of that. This first part of the question is a familiarization exercise with skeletal formulae, and you need to become confident at identifying different representations of the same molecule. So for part AI we're looking for ethene. We know that ethene's got 2 carbons bonded together with a double bond. However, all the molecules in table 1 have at least 4 carbons, so it's impossible for ethene to be present. So we know that the answer that we need to write down there is 0. When we're looking for butane, we're looking for 4 carbons bonded together in a linear chain and no double bonds. So if we go over these molecules, 1 and 2 have got a double bond present, so it can't be them. Molecule 3 has got 4 carbons, even though it's not drawn in a linear chain, it's bonded together in a linear chain, so that is butane. Molecule number 4 has got more than 4 carbons, so that cannot be butane. But molecule number 5, again, all of these represent carbon atoms, and we've got 4 bonded together in a straight chain, so again that is going to be butane. Molecule 6 and molecule 7 have got more than 4 carbon atoms, so it cannot be them. Molecule number 8 has got 4 carbon atoms, but there is a double bond in the middle, so that would be butene. And molecule number 9 again has clearly too many carbon atoms to be butane. So moving on to the third molecule we have here, we can look at the main chain. So the longest chain in the molecule is 6 carbon atoms long, and there's a branch coming off the third atom if we count from one of the sides. Going through the molecules in table 1 in turn, molecules 1, 2 and 3, the longest chain is 4 atoms long, so even though molecule 2 has got more than 4 atoms, the longest chain is 4 atoms long. Molecule 4, the longest chain is 1, 2, 3, 4, 5, 6, so that fits, and we've got a methyl group coming off the third atom over here if you count from this end, so it seems that that matches the criterion for being molecule III. Molecule number 5 is butane, as we said earlier, it's too short. Molecule number 6, 1, 2, 3, 4, 5, 6 carbon atoms in a row, and the methyl group on the third atom. So again, that's consistent with being molecule number III. Molecule number 7 doesn't have any branches, cannot be this. Molecule number 8 has got double bonds, doesn't match. Molecule number 9, the longest chain is 1, 2, 3, 4, 5, 6 atoms long again, and that methyl group is on the third atom if we count from this end. So again, that's consistent with being molecule number III. Finally, we need to identify the molecules in table 1 which match trans-butene structure. So remember, in trans-butene we've got a double bond in the middle of a 4 carbon chain, and then we've got the 2 substituents on either end of the double bond on opposite sides. So that is consistent with structure 1 and structure 8. Structure 1 and 8 are the same, it's just rotated slightly. It doesn't match any of the others. The only other molecule that's got a double bond is number 2 here, but clearly that has more than 4 carbon atoms, so it cannot be trans-butene. This question is hopefully just straightforward A-level material, but you should be familiar with this reaction of HBr with alkenes, and it's an electrophilic addition. The question spends quite a lot of time in actually talking you through the mechanism that's going on here, so even if you haven't quite covered this at A-level or you are not so sure about it, the detail is all there, so make sure you read the question carefully and reconcile that with what you know already so that you can tackle the later parts of the question. Right, now part C, you need to draw out the alkenes which could have led to the formation of this bromoalkane when it reacted with HBr. Based on the reading that you've done in the question, you know that the double bond must have been here or here. Now, how does that give us 3 possible alkenes rather than just 2? Well, if the double bond is over here, in the middle of the molecule, we can have it present as both the cis or the trans isomer, so it gives rise to 3 different structures. So let's just draw them out to make sure we know what we're talking about. So one is going to be the isomer with the double bond on the end, and we've got 2 isomers with the double bond in the middle. One is the trans isomer, and the other one is the cis isomer. Okay, so in part D, we now need to work out which of these products we can get based on the reaction with HBr of these different alkenes. So it's worth looking at the carbon skeletons first, because bear in mind that the carbon skeleton cannot change when we react with HBr, and we've fundamentally got 2 different types here. So we've got I and IV, which have both got a long chain of 4 carbon atoms. We've got II and III, which have got a chain of 5 carbon atoms, and both of them have got a methyl group coming off, both of these types. But if we can just look in table 2, we see that some of the molecules have got a carbon chain that's 5 atoms long, and others have one that's 4 atoms long, and so it immediately narrows down the possibilities that we actually need to look at. So for molecule I, we only need to look at the 4 carbon chain long molecules in table 2. That is actually, so that's molecule 13 here, molecule 16, and molecule 17. All the other ones have got 5 carbons in their longest chain. So which of 13, 16 and 17 can we actually get from molecule I? Well, the Br can end up either on this atom or on this atom following the reaction with HBr, which gives us molecule 16 and molecule 13 respectively. We cannot get molecule 17 by using molecule Y, because the Br would have to end up on one of these 2 atoms. Now if we look at molecule IV next, because that's the other one with 4 atoms in its longest chain, the bromine in this case could end up either here or here, and that will give us molecule 17 and molecule 16 respectively. In this case we cannot get molecule 13 because the Br would have to be added to this atom. Okay, hopefully now we've seen how it works for some of the smaller molecules, it'll be easier to do the longer chain molecules as well. So in molecule II, the bromine could end up on this atom or on this atom, which will correspond to molecule 18 and molecule 14 respectively. Now in the other ones we cannot get, because all the other products are different when we can only ever have 2 products here. For molecule III, the Br can be here or here, and if we look at that again, that means we can get molecule 12 and molecule 18, and we cannot get any of the other ones. Alright, now there's a bit of reading in this question again. It's actually quite helpful, and it talks you through how to follow the changes that take place in the molecule, and in particular that you can trace the carbon skeleton and what happens to it along, and that you're then asked to use this strategy in the following question, so make sure you read this part. Okay, so looking at the scheme of reactions here, I'm going to focus in on this part and try to work out what the structure of carbocation B+ is. And only after I've done that can I really tackle these other parts to get to C+ and D+. So in order to work out the structure of B+, I'm going to have to use the techniques that you've just been reading about and try and match the chain that I see in carbocation A to the chain that has really become a ring in alpha terpineol over here. So comparing carbocation A plus and alpha terpineol, what jumps out of me is this two methyl groups attached to a carbon, which I can see here in the alpha terpineol as well. And I also noticed that I've got a double bond which has a methyl group attached to it, and I see the same thing over here. So if I'm going to try and colour them in different colours, this is that, and this is this. So for my labels to work, if this is A, B, C, then this is going to have to be D, because C is only bonded to D and the two methyl groups. And then one way or the other, I'm going to have E, because D is bonded to E and we're not breaking any carbon-carbon bonds here. But if this were E, then this would have to be F, and F doesn't have this double bond attached. So if we try and go the other way around, if this is D, E, F, G, and we can see that that's working out quite nicely because we're now in the yellow ring, and this is H, this is I, and this is J. So I've now carried over the labelling to this diagram over here. It's just what we've talked through a minute ago, and we can redraw the original molecule as this shape, which resembles what we're getting as the final product. This now allows me to see very clearly what the change that's taking place between this carbocation and this product actually is. So I'm forming a bond between D and J, a carbon-carbon bond which wasn't there before, and instead of having this double bond, I now have a single bond and an OH. However, we know that the reaction goes in two steps. The original carbocation first cyclizes, i.e. we form a ring, and then we get the second step where water is added and we get deprotonation happening. So in order for this to cyclize, the double bond is going to have to break, and instead we're going to form a bond between D and J. I've now drawn in the curly arrow to indicate that this is happening, and hopefully it's now possible to follow this scheme despite the fact that it looked so complicated at the start. To work out the structures of the C plus and D plus ions, we now need to look at the structure of the B plus ion that we've already worked out and compare this to the boronil and the beta pinene structures respectively. So what are the common features that we see now? Well, in fact, the two methyl groups attached to an atom thing seems to be present here again, and the individual methyl groups sticking out, I can see that here. So that means that this will be our C atom again, which you know is bonded to a D atom. Now, if this is the H and G part, then this cannot be the D atom, so this will have to be the D atom, and that's consistent because this is these are opposite sides of the ring, and D and G are on opposite sides of this ring. Now, we end up with this OH group over here, which seems to tell us that the double bond that's over here was originally here. So that means that this is I and this is J. On the other side we've got the G bonded to F, and then this is E, which is bonded back to D, so everything's consistent because we expect there to be an ED bond as here. To work out the structure of the carbocation C+, which we'll get by cyclizing carbocation B+ once again, we could redraw it similarly to how we've done previously, so that it looks like the final product that we have over here. However, in this case it is also relatively easy to see which bond we are forming. We're forming a GC bond, which we didn't have previously. So we know that we're going to use the double bond again, and we're going to attack the positive charge similarly to how we did previously. So we can draw out the curly arrow mechanism and follow it through, and then draw out the resulting carbocation C+ in a way that's similar to the product. And when we do that, this is what we end up with. This is the structure of the carbocation C+, and we see that the positive charge is now located on carbon I, which makes sense because that's the other atom that was involved in the double bond, not the one that we ended up bonding through, which was G. Right now we're looking at forming beta pinene via a new carbocation intermediate called D+, which involves a different cyclization, again starting with carbocation B+, which we had previously. We need to match up the carbon atoms as before, so we need to look at the structure of B+ we have here and the new product of interest and see whether we can find common features. Now, as it turns out, this 2-methyl group pattern is repeated again here, so that's a common feature we see. Now the rest of the molecule doesn't match up as nicely as things did previously, but we do in fact have another carbon sticking out of a ring, as we had H previously, so we might tentatively match up those two. So counting from C over here, if this were to be D, and we think this is G, then there's nowhere for E and F to be. So if this is C, this would have to be D with this being G, and that would be consistent with having E here and F here. GH. What else is G bonded to? It's bonded to I. And I is bonded to J, is bonded to D, so that would all work out nicely. So I've now put in the labels, and we need to compare the structures of the original carbocation B+ and the product to see which is the newly formed carbon-carbon bond, and we'll find that it's the Ci bond over here. So that will allow us to draw the mechanism again. We're going to do a similar thing once more using the double bond, going through the I atom here, so using that for bonding and attacking this carbon atom C. So I've now followed through that curly arrow and drawn out the product in a way that's similar to the final product, the beta pinene in this case. And we see that the positive charge is in this case on the G atom, which is once more consistent with having had that involved in the double bond, but not having bonded through that G. Now note that the follow-up reaction in this case was different, and we lost a proton from here, so we deprotonate to form a double bond. Part H at first sight looks really challenging because we've got compound T, which is quite a big molecule. However, if you look at the reaction that's happening to form cation U+, it's actually just a protonation step. It's only got +H+ written on the arrow. So we need to look at compound T and work out where would be the easiest place to protonate, what's the most basic group. If we consider that will have to be the OH in the molecule there. So if we try and draw out the product, obviously if it asks for the full product you'll have to draw out the full thing in the exam, but I'm just going to draw out this ring here, cut off the molecule there. The only change is that we have now got an additional proton on this OH group, and don't forget we've also now got a positive charge. Part I is very similar to what we've done before, because you need to look at carbocation W+ and match up the carbon atoms in it with those in carbocation V+, so that you can identify the CC bonds which are new. So which features do the two molecules have in common? Well, I've got this 5-membered ring over here which has a double bond and 2 methyl groups sticking out. I've got the same thing in carbocation W+ over here. I can in fact circle that already because they're going to match. I've also got this triple bond near the end of carbocation V+. Now I don't have a triple bond in carbocation W+, but I do have this double bond with a positive charge, and it's possible that this has become that. So if I go with that, then this will be atom A, B, C. Now, I'm not quite sure which way to go around the ring, but there's a methyl group sticking out here that's not going to be D, because D's only got 2 bonds in carbocation B+. Even if we form one additional bond to it, it's unlikely that we formed one bond to form a methyl group. That wouldn't be a cyclization reaction. So this will be D, E, F. Now, G has that methyl group sticking out in carbocation B+, which makes it consistent with being this atom over here. Then this is H. So if we then continue following around the ring, we cannot go this way because this is C already. It's going to be I, J, K. Now L doesn't have a methyl group attached, so L is likely to be over here. M, N, O. Now we are in that green ring and we can match up the atoms within it individually. Q is on the double bond, so let's go with this being Q. P is on the methyl group sticking out, and then R, S, T, and finally U in the other methyl group. So I've now drawn in the labels, and hopefully that makes it easier to see where the new bonds have come from. So we said we follow the chain route A, B, C, D, E, F, G. Now you'll notice there's a new GC bond here, which wasn't there previously in the original carbocation V+. Alright, so now we follow the ring further. H is just a branch coming off, but if we go I, J, K, K has now got 3 bonds to carbon atoms. It was previously only bonded to J and L. It has now picked up an additional bond to T as well. Alright, if you look further, L has also got 3 bonds now. Previously it was bonded to K and M. Now it's bonded to F as well. So we've got a new FL bond as well. Alright, and then we continue around N, O, and this structure, as we said before, was there previously. So in summary, the new bonds are CG, FL, and KT. Alright, we've now reached the final part of the question, part J, and I'm afraid this part is really quite tricky, depending on what reactions you've seen before and how familiar you are with following syntheses like this. One very useful thing is that even though there are a few intermediates and we don't know their structures, we're given the structure at the start, the carbocation W+, and at the end, and we can look at what changes have happened in these 4 steps that we see in the middle. Well, this part hasn't changed at all, you'll notice. This part has become a ketone group here, and the thing that changes most is this 5-membered ring now becomes a 6-membered ring. There does appear to be a carbon-carbon double bond again, and there is now a ketone group as well though. Okay, so looking at what we're told about compound X, it says IR 1720 wave numbers. Now, hopefully you'll know now that that is a value that's representative of a carbon-oxygen double bond stretch. So we'd expect to see some kind of carbonyl in compound X. Looking back at carbocation W+, there is no oxygen in this molecule currently, so it's clear that will have to come from the water that we're reacting with. The only reaction centers here are the 2 double bonds, and this double bond is different. Now, if you were to protonate a normal double bond, you'll just form an OH group. You won't end up with a carbon-oxygen double bond. However, you've not seen reactions with charged double bonds before, so given we see a different product, it's sensible to assume that it happens because we get reaction at a different center here, and it's different because it's now got a positive charge. It'll be difficult to suggest how that carbonyl forms here without extra knowledge, but if we look at the product, we see that this is where the carbonyl is. So you might hazard a guess that that is actually what forms in this reaction here. As before, I'm not going to copy out the whole molecule, although you might have to do that in the exam, but I'll just draw out this bit at the end where I'm going to assume that I now see this ketone and the double bond has disappeared. The carbon-carbon double bond has disappeared, and I've got a carbon-oxygen double bond instead. In terms of the stereochemistry, note that we've got a few chiral centers in the original carbocation W+, so it's possible that when it reacts, even though it's not reacting with chiral reagents here, it is forming further chiral centers and not forming racemic mixtures of them. So it's possible that we've got more of the specific stereoisomer that's drawn out here with the H going down into the page. So I'm just going to draw it out like that here as well. The information we're given about compound Y might not seem that useful because we're given the elemental analysis, which just means the percentage of the individual elements present by mass. But because we know the number of carbons in these molecules, because the carbon skeleton doesn't change, we can actually work out the full molecular formula from this. So we know that the number of carbons was 21 to start off with. It's going to be 21 in the end. So if we write down C21, now if you remember what you usually do for elemental analysis is you divide the percentage of here by the relative atomic mass of that particular element. So 75.86 divided by 12.01, that gives you a value of about 6.32, and if you divide that by 21, you get the scaling factor that you need to use on all the other elements, and the scaling factor is around 3.32. So to work out the number of hydrogens present, I'm going to take 9.70, I'm going to divide that by the relative atomic mass of hydrogen, which is about 1.008, and remember in this periodic table we've got a few more significant figures to use. And I'm going to scale that up by this factor of 3.32, which gives me an answer of about 32. And if I apply this technique to the oxygen, I get 14.44 divided by 16 times 3.32, which gives me more or less exactly 3. We know that the molecular formula of the carbocation W+ was C21H31+. What then changed looking at compound X was that we've introduced an additional oxygen and in fact a hydrogen as well, and we've lost the charge. So you can see that by looking at plus H2 and minus H+, that means we've overall added one H, one O, and removed the positive charge. So the molecular formula for compound X was C21H32O. Now looking at compound Y, we've retained the number of carbons and the number of hydrogens, and we've just increased the number of oxygens by 2. Now looking at what it also has told us in the question about in forming compound Y, ozone breaks a carbon-carbon double bond and forms 2 new carbon-oxygen double bonds. We didn't have a carbon-carbon double bond up here anymore in compound X because it's become a ketone. The only carbon-carbon double bond remaining in compound X is the one that was down here in carbocation W+. So we don't know exactly how we're going to form the 2 new carbon-oxygen double bonds, but a good assumption would be that we break the bond and we form a double bond O coming off each of the carbons here and here. Now again, I'm just going to draw a small part of the molecule here. So in this case, this is the 6-membered ring, which is the furthest to the left. I'm going to break off the molecule there. And originally we had this 5-membered ring attached, but the 5-membered ring is now broken open, and instead we've got, counting along the atoms, 1, 2, 3. That's this atom over here, which is now got a double bond to a carbon instead of to an oxygen, and obviously it keeps that methyl group. The other part of the double bond over here, that's this atom over here, and that one has also gained an oxygen, a double bond to oxygen. So it looks a bit like this. I've nearly forgotten the methyl group that's sticking out here. That's obviously also still there. And the rest of compound Y is as before, as it was in compound X. Remember when you're copying out the structure that you do copy out the structure of compound X, the top bit will now look like this, not like this. Right now I think this very last part is very tricky if you've not seen a similar question before, because you're essentially deprotonating the molecule, but it's not at all obvious where you should deprotonate, and definitely at A level you've not come across this kind of group being acidic. But protons that are attached to carbons next to a carbon-oxygen double bond, so the ones that are attached to here, here and here, are acidic, and this one is going to be the most acidic, most available proton, and that one of the protons that's attached to this carbon is the one that's going to be removed here. Now in fact there's also an acidic proton up here in the top of the molecule, but that cannot lead through to the further reaction which forms the final ring, so that's not the one we're focusing on. We're deprotonating this part of the molecule, so the product has that part looking a bit like this. You'll notice that all that's changed is that we've now got a negative charge on that atom that I indicated we get the deprotonation occurring at. And we don't need to worry about the mechanism for the cyclization that follows, as the question doesn't ask for this. And as I said, I think this is a very hard part of the question, because without knowing how this happens, it's very difficult to see why it should happen. However, you do know that you have to form this 6-membered ring, and that will have to involve this carbon, which previously wasn't involved in the reaction. It was just a methyl group that was sticking out. In order to involve it in the reaction, we need to do something with it, because generally a methyl group is not just going to react. And if we deprotonate it here, then it becomes nucleophilic and potentially will be able to carry out an attack and participate in the reaction to form that 6-membered ring. Okay, so that's the end of question 2. I hope you found this video useful, and again I've included the reference that was given in the original paper to the question paper, but this is the reference to the research paper that this question is based on, which again you can refer to for further information if you like. Anyway, thanks for watching, and bye for now.